Hello, this is part 2 of module 4.4. So now, after all that calculations and all that plotting, so how do we use those plots anyway? So now, how do we choose or how do we use that? So let's just redefine that the quiescent point, it defines the characteristics of the amplifier. In the large signal domain, so in the domain, the VTC domain, so the Q point is usually decided based on the desired DC gain and voltage swing of the amplifier. So let's define. The DC gain is the quantity that defines the gain of the amplifier at low frequencies where the transistor capacitances act as open circuits. So, when we move to module 6, we will see the effects of these capacitances, but it is expected that the gain will be less than DC gain at higher frequencies, because all these parasitic capacitances or all these transistor capacitances is expected to have lower impedances. So next, the output voltage swing. So the output voltage swing is the output voltage range that the output signal can have. And then the input voltage swing is the input voltage range that the input signal can have. So now, next part. So let's look further into the swing, the input and output swing. So where does this come from? So because real amplifiers have a finite power source, so it's expected that it will saturate when the output signal reaches the power source's limits. So we have a VDD and we have ground, or we can change this to VDD or negative VDD, but the point is they are finite. It is not infinite. So to preserve the signal, so in order for the signal to be accurate, so we expect that the output must be limited to these limits, L minus and L plus. So this, when we look at this plot, so L plus usually is the VDD here, and then L minus usually is the ground or the negative VDD, depending on what voltage is this terminal in. Because if the amplifier is biased to have anything greater than L plus, it is expected that instead of following, for example, this one, instead of following the ideal performance here, because it cannot expand from the value of L plus, it will clip here and here. So that is not a good behavior, because we don't want to lose signal integrity due to that. And then looking at the other side other side here, if we have an output signal here, if we have a value higher than lower than L minus, it is expected that it will clip to L minus here, just like here, as shown here, this one. So instead of extending from here to here, it will clip to the value of L minus. So this idea can be used to define the amplifier's output voltage swing. So ideally, you want to work in the middle, because the middle of the peaks or the limits. So how do we now consider the input side? So because the output is limited from L plus to L minus, and we can now find that the input is limited to L minus over the gain at that point, and then L plus over the gain also. So because, as you can see here, remember what you did before, if this is our signal, if we expect that the gain is in a certain value greater and we get an output greater than the limits, we will get a clip signal because this input is too high. So now, if we decrease this input, for example, to this one, to number 1, this one, and it is within the limits, we will get a very, very nice signal here. So that's why we have to also consider what kind of input or what magnitude is the input in. So how do we apply this? So for example, this one. If we consider a common source amplifier, shown here, and remember from the earlier discussion, this is the voltage transfer characteristic of a common source amplifier. So the input and output swing can be derived by using this VTC, because as you can see, if the transistor is off, it will be forced to go to VDD, which is the maximum output voltage limit. So this is L plus, and then the common source has a ground, which is shown here. So it is the minimum output voltage limit. It's expected that this one will be asymptotic to ground. So most likely the minimum output voltage limit is 0. So if we consider this, so if we bias this, for example, if we introduce a DC voltage here to be at point A here, we will get that the maximum output swing of this of the signal output is at VDD minus some certain VP. So the output signal is limited to VDD minus VP. Anything greater than, if we force the input DC signal to have a if we force the input signal to be higher than a certain value, it is expected that it will clip in the top side because of this VDD. So therefore the maximum input swing can be shown to be VTHN, because VTHN is the point where it reaches VDD to a certain value VHA, shown here. Okay? So we are limited by the VDD here. So next up, how about we bias it to a certain very, very low value? So for example, let's bias it here at VB, at B, point B. So if we introduce a input DC voltage to be here, shown in point B, the main problem now is that we expect that the output swing is limited to a certain VPB here, and then to 0, because this is almost asymptotic to 0. So this is almost 0. And therefore, the input swing, the input side is limited to certain Vx minus VLB. So we are limited here because of reaching the lower limit here. So ideally, if you want to maximize your swing, you want to bias it at a certain point C, where V out equals 1/2 of the supply, just like what we discussed earlier, that if you want to maximize the swings, you want to operate at the middle. So the maximum output swing now is VDD minus, this is almost 0. So this is not 0, 0, because we cannot force this to be 0. So we just approximate this to be 0. So the maximum output swing is approximately VDD, and the input swing can be is very high also, to be some certain value Vx and VTHN. Okay, so if you want to have maximum voltage swing, the output side, and conversely to the input side, you want to bias your amplifier in the middle here, point C. So now, to maximize the gain naman, you want to use the gain versus V in plot, shown here. So if you use this, you can see that you do not want to bias your amplifier in the cutoff and the linear or triad region, because we have no gain there. So if you bias the amplifier at a certain voltage Vm, you will get the maximum gain that this amplifier can have. If you bias it as Vn1 or Vn2, you will expect a certain gain An. So remember that the negative sign denotes a 180-degree phase shift and does not imply a lower output amplitude. Okay? So this changes if the gain is converted to dB, but for this case, this is not dB. This is just normal. This is just gain. So if you want to have max gain, you bias at VM. But take note, you have to also look at the VTC, because it is possible that VM is not the quiescent point or the Q point that gives you the maximum swing also. So that is not true. So you have to trade off some gain for some swing, and also you have to trade off some swing for some gain. So you have to consider those trade-offs. So it is not always equal. VM is not always the input signal that gives you 1/2 VDD. So you have to consider that as a designer. Okay. So let's do a sample problem just for you to have an idea. So given this circuit, so this is an NMOS transistor and a common source, and it is characterized to have 7,000 microamps per volt squared and VTH and 2.6. Find the following. First step, you have to find the VTC. So as you can see, the threshold voltage is 0.6. So therefore, any input, if you substitute any DC voltage less than 0.6, you will get a VDD output. And then, the next step is to find the voltage input where the transistor is in the edge of saturation. So you must find Vout that gives you Vout and Vin that gives you the edge of saturation. Because remember that there's a point here that that defines where the amplifier is in saturation and in the linear region. So what do? You calculate VDS, calculate calculate VDS. And remember that because this is the edge of saturation, the desired input voltage is the only value where the saturation current is the same as the calculated current using the linear expression, because this is the edge. So that means that when you use the saturation current equation and the linear equation current, you'll get the same. But we're gonna use the linear one. So this is this one. So we use these equations. So we substitute everything. So we substitute because we want the because we want Vout to be equal to VDSat, right? And then VDS is also Vout, so we want that to be VDSat, and this one too, VDSat. So we just substitute. So Vin minus VTH, so this Vin is VGS, right? So this is VDSat equals VDD minus the equation of the current times RD, which is shown here. Then we solve, we will get this equation. Then to solve for Vx, we just solve this quadratic equation. We get a negative and a positive solution. Of course, you want to have the positive side. And we substitute this back here. So Vx equals Vn minus VTHn. And we will get 1.377 volts. So if we reach 1.377 volts, the amplifier is in the edge of saturation, shown here. So 377, we just round it up, so 1.38 here. So that means that this is the amplifier VTC. And then if the amplifier is biased to have 1.38 volts here, the output DC is 0.78, because remember 0.78 is VGS minus VTH, which is the VDSat. Okay? Now this is the amplifier VTC. So next, how do we find the gain at certain voltage values? So how do we do this? So remember, the gain is the derivative function, right? So what we do is we define a certain value, delta V, a very, very low voltage, because remember, when we find derivatives, we want to minimize this delta V and find the tangent line. But for simplicity's sake, let's just define a certain delta V. And then for a certain Vn, so for this one, for example, this 0.8, so 0.8 plus, let's use 5 millivolts. So this 0.8 plus 5 millivolts minus the value of Vout at 0.8 minus 5 millivolts over twice 5 millivolts. So, for example, this one. So, at gain at 0.8 is just the output voltage when the input voltage is 0.805 minus the output voltage when the input is 0.795 over 0.01 because twice delta V is 0.01. So we know from the VTC that at 0.8 here, the transistor is in saturation, so we use the saturation equations. So this one. We just substitute, solve for ID sat, and then we substitute back here. We will get these voltages, and then we subtract. And we get that the gain is 2.8 at that certain point. So as you can see, at 0.8 here, if we introduce a small signal here, there, the output has a gain of 2.8 here. Okay? Next up, if we want to bias this at 1.1, we just do everything again. So 1.1 plus 5 millivolts minus 1.1 minus 5 millivolts here over 0.01. And then we find the input at 1.105 and 1.095. So we just repeat. So all you have to do is substitute V in here, solve for current, substitute here, and then you can solve for output. So you get this one. And then you just redo everything. So you get the gain of 7. So just to give you an idea, if we put the voltage here, 1.1, and we introduce a small signal current, a small signal voltage there, we get approximately a gain of 7 here. Now, what do we need to do to achieve maximum output swing? So find the input needed for maximum output swing. So remember that the maximum output swing occurs if the DC output is between maximum output voltage and input voltage. So what does this mean? So V out equals 1/2 VDD. Just like what we said earlier, so 2.5. So if we put 2.5 here, in V out, we just solve for the value of V in. So remember, if this is a 2.5, we expect that this resistor is in saturation. So we just substitute here. So V out equals VDD minus RD IDS sat. And then V out is 1/2, shown here. And then you get this equation. And you substitute everything given this one. And the input is unknown. So that is the variable. VTH is given. The process conductance is given. Resistance is given. The supply is given. You substitute and you get 1.198 volts. So as you can see, if we bias this transistor to have 1.198 volts, we will get maximum output swing. So the summary. So the amplifiers aid processing of weak signals. So there are 3 basic MOS amplifier topologies: common source, common drain, and common gate. So the common source amplifier are inverting amplifiers, while common gate and common drain amplifiers are non-inverting. Amplifiers can be characterized using VTC and its gain versus input voltage plots. The amplifier gain and voltage swings can be found using its DC characterization plots. Okay? So thank you for listening.